The next sorting algorithm that we will be implementing is selection sorting algorithm. But before we go ahead and try to implement it, let's just try to recollect what exactly we have done as part of the bubble sorting algorithm and what is something that we will be doing different as part of this selection sorting algorithm, so that it will give you much more great context. So as part of the bubble sorting algorithm, we tried comparing the two adjacent values from the beginning of the array till the end of the array. If we do that logic once, we have bubbled the largest value to the end of the array. By repeating the same logic for all the values that we have in the array, that means that by repeating the same process for n number of times, where n is nothing but the size of the array, we have sorted the entire array in the ascending order. So the process involves basically comparing the two adjacent elements. If at all they are not properly arranged, we are basically swapping them. As a result, in the entire comparison logic that we are doing, there could be a lot of swapping operations, right? Which is nothing but they are trying to bring down the efficiency of bubble sorting algorithm. As a result, since anyway we are comparing the values, right? Why are we swapping those values then and there only? Why don't we find the appropriate value after comparing all the values, and then why don't we swap only once in the end? Okay, so that is the thought process behind selection sorting algorithm. So as part of the selection sorting algorithm, what exactly we will do is we will try to find the appropriate value for each and every position that we have in the array from the remaining values of the array that needs to be processed. As a result, since we are selecting the value for each and every position that we have in the array, the name selection sorting comes into the picture, as we are selecting the perfect value for each and every position. Okay, just like bubble sorting algorithm, selection sorting algorithm is also one of the in-place sorting algorithm only. That means that whatever the array that we get in the same array itself, by comparing and swapping, we will try to sort the entire array either in the ascending order or in the descending order. Okay, so that is something to remember. Now let's just try to implement this selection sorting algorithm. Let's just try to dry run our logic on this example array that we have here, and let's just try to sort it in the ascending order. So the array of values that we have got here are 1, 4, -5, 3, 7 and -2, and these values are available at indexes 0, 1, 2, 3, 4, 5. Now our aim is to sort this array in the ascending order. That means that for index 0 we need to fill it with the least value, and on the index 1 we need to fill it with the next greater value. Like that we have to fill each and every position, so that in the end the array is sorted in the ascending order. Okay, now let's get started and let's just try to dry run our logic. Here the first index that needs to be filled with its appropriate value is index 0. Right now what I will do is, whatever the value that we already have at that particular index, right, it could be the perfect value for that particular position. That's the reason why what I will do is I will keep track of a variable called current index or something like that, which will basically give us what is the appropriate value available index. That means that if we go to this current index variable, we will find the appropriate value for the index that we are trying to fill in. Okay, right now since I am starting with index 0, I will be initializing it with 0. Now what we will do is, we need to fill this index 0 with its perfect value, right? So we will try to compare the remaining values whatever we haven't processed yet for finding the perfect value. For that what we will do is, the value at index 0 gets compared with all the values that we haven't processed yet. That means that whatever the value we have at index 0, that means 1 is compared with 4. Obviously 1 is smaller than 4, right? That means that if we are trying to sort the array in the ascending order, there is no chance that 4 will come before 1. So 1 could be the appropriate value as of now. So current index will still remain 0 only. Now again what we will do, the value at current index 0 gets compared with the next value, which is nothing but the value at index 2. That means 1 is comparing with minus 5. Obviously minus 5 is smaller than 1, right? That's the reason why the appropriate value could be minus 5, which is available at index 2. So we will update the current index to 2. Now the value that needs to be compared is basically the value at index 3 and the value at index 2, because the smallest value is no longer 1. The smallest value is minus 5 and is available at index 2, and the non-processed elements are from index 3 to the remaining part of the array. That's the reason why minus 5 gets compared with 3. Obviously minus 5 is smaller than 3, right? So minus 5 is the appropriate value. So we will not update the current index, which is holding the position where we could find the appropriate value for the index that we are processing, which is nothing but index 0. Now what we will do, again minus 5 is getting compared with the value at index 4, which is nothing but 7. Obviously 7 is greater than minus 5, so minus 5 is the perfect value as of now. Again this minus 5 is getting compared with the next element that we have, which is nothing but minus 2. Obviously minus 5 is smaller than minus 2, right? So minus 5 is the perfect value as of now, and there are no more elements that we can compare. Basically we have reached the end of the array while comparing. So for index 0, the perfect value is available at index 2, which is available in this current index variable. So now what we will do is, the value we need to fill in the index 0. That means that we are trying to find the perfect value for index 0, right? And it is available at index 2. So what we will do is, we will swap these two values. Okay, that means that value at index 0 gets swapped with the value at index 2. As a result, the resulting array will be minus 5, 4, 1, 3, 7 and minus 2. Right now we have filled the index 0 with its perfect value. So the remaining values we need to find the perfect value and sort. So the next position that we need to fill is 1. So whatever the value we have at index 1 could be the perfect value for its position. That's why we will initialize current index with 1 when we get started with the next iteration. And we need to compare it with the remaining values we have in the array for finding its perfect value, right? That's the reason why the value at index 1, which is nothing but 4, gets compared with the remaining values. That means that we need to compare it with the element at second index, which is nothing but 1. So 4 and 1 gets compared. Obviously 1 is smaller than 4, right? So 1 could be the perfect value for the index 1. So we will update the current index to 2, because the smaller value is available at index 2 than what we already have at index 1, which is nothing but 4. So what we need to do, we need to continue the comparing operation, right? So the value at index 2, that is nothing but 1, gets compared with the remaining values that we haven't compared yet. That means that the values at index 3, 4, 5. So right now let's compare the value 1 with 3. Obviously 1 is smaller than 3. So 1 is the proper value as of now for the index 1. Now again, so the value at index 2 gets compared with the next value, which is 7. Obviously 7 is greater than 1, right? So far still 1 is the perfect value and is available at index 2. Now this 1 again gets compared with the value minus 2. Obviously minus 2 is smaller than 1, right? That means that the current index, that means that the appropriate value for the index 1 is available at index 5, okay, which is nothing but minus 2. To continue the comparison further, there are no more elements in the array, right? That means that for the index 1 that we are trying to fill, its appropriate value is available at index 5. That's the reason why what we will do is, we will swap these two values. The resulting array will be minus 5, minus 2, 1, 3, 7 and 4. Okay, so right now first two values are filled to its perfect position. So the next position that we need to fill is index 2, and the remaining values are that we need to compare are 3, 4, 5. So current index variable, since we are trying to fill its perfect value for the index 2, we will initialize it with 2 only. Now the value 1 gets compared with next uncompared value, which is nothing but 3. Obviously 1 is smaller than 3, right? So the appropriate value is still available at index 2 only. Again, the value at index 2 gets compared with the value at index 4, which is having 7. So 1 is the smallest value, and as a result we will go on to comparing 1 again with the value at index 5, which is having a value of 4. So far we have compared with the remaining all values we have in the array, and its perfect value is available at index 2 only. So even if we swap, the same position is getting swapped, right? As a result, the resulting array will be -5, -2, 1, 3, 7 and 4. Out of all these 6 values, we have sorted first 3 values. The next position that we need to fill is index 3, and the values that we need to find are from index 4 and 5. As a result, current index we will initialize it with 3, and the value we have at index 3, which is nothing but 3, gets compared with value at index 4, which is nothing but 7. Obviously 3 is smaller than 7, so 3 could be its perfect value. That's the reason why we will continue the comparison, since we have one more value left in the array that needs to be compared. Here the index 3 has value of 3 and index 5 has a value of 4. Obviously 3 is smaller than 4, right? So for the index 3, the appropriate value is available at index 3 only. As a result, even if we swap, the resulting array will be -5, -2, 1, 3, 7 and 4. Now we have all these values in the sorted fashion. The next question that needs to be filled is index 4, and the value that we need to compare it is, which is nothing but available at index 5. Now current index, since we are trying to fill it for index 4, whatever the value we have at that position could be the smallest value, I mean its perfect value. That's the reason why current index we will initialize it with 4, and the value at current index 4 gets compared with the value at index 5. Obviously 4 is smaller than 7, right? That means 4 should come first and 7 should come later. As a result, current index we will update it with index 5, and there are no more values to compare. As a result, what we will do is we will try to swap the values available at these two indexes. So if we swap the values, the resulting array that we will get will be -5, -2, 1, 3, 4 and 7. And the last position, if you observe here, right, anyway it itself have been moved to its perfect value. As a result, in the end, if you see, we have processed each and every index that needs to be filled with its perfect value, and we have completed the entire logic. There are no more elements that needs to be repeated with the same logic. As a result, if you see here, whatever the output that we have got is sorted in the ascending order. Okay, so that is the selection sorting algorithm. So as part of the selection sorting algorithm, what exactly we did? First, we chose the index that needs to be filled with its perfect value, and we tried comparing it with the remaining values that needs to be searched for its appropriate value. If so, if at all, if we find an appropriate value for a particular position that we are trying to fill in, we tried swapping in the end. So if you observe here, we are only comparing and we are keeping track of the index where we could find the perfect value for the position that we are trying to search and fill. As a result, we are eliminating all the swapping logics immediately as soon as we compare. Rather, once we search the entire array, in the end, only once we are swapping. Okay, so that's how we are bringing in the efficiency in the selection sorting algorithm, by eliminating all the swapping logics then and there only. Okay, so one more thing, anyway, if you see here, as we compared and as we implemented, we achieved the sorted array in the input array that we have got itself. As a result, it is one of the in-place sorting algorithms only. Okay, so those are the steps that we will be following for implementing the selection sorting algorithm. Now that we know the steps involved in the selection sorting algorithm, let's just quickly write the pseudocode of it, and let's move on to the implementation and validation of the selection sorting implementation. For that, anyway, to write the pseudocode, first of all, in the implementation, what we will do is we will try to write one function called selection sorting. It will basically take the array of values. In the end, we will basically return the array of values in which all the values are sorted in the ascending order. Okay, as part of the first step, what I will do is let me just read the length of the array that I have got, so that I can basically use that while writing the iterative statements. So as part of the selection sorting algorithm, what exactly we are doing? We are first choosing the appropriate value for each and every index, right? So first of all, basically we need to write a logic which will basically choose the indexes from 0 till the very last index that we have in the array. So for that, what I will do is I will simply write a for loop. Let's name it as I. It basically starts from the very first index in the array, which is nothing but 0, and it basically executes till the very last index. That means that it needs to execute till the last index, which is nothing but n minus 1. As a result, I'm executing it till less than n. In each and every step, I need to move on to the next index, right? Because once I fill the value for its position, I should move on to filling the appropriate value for the next indexes till we do the same thing for all the positions that we have in the array. That's the reason why I'm incrementing it by 1. Now, if you remember the next step, whatever the value we already have at this index itself, that we are assuming it could be the appropriate value. That's why here I will define one variable called current index or something like that, and I'm going to initialize it with I itself. Okay, because it is the index, it is not the value. Now, what we need to do for finding the appropriate value for this index, whatever the values that are available from the next index till the very last value we have in the array, we need to compare it, and if at all the value that we are comparing is smaller than whatever the value we have at this current index, it could be the appropriate value. For comparing that, what I will do, I will need to run one more for loop, and this for loop needs to run from the next indexes that needs to be compared. That's why it will always start from I plus 1th index, and j, it needs to run for remaining all values for the comparison, right? So it also needs to run till very last index, and in each and every step we need to move on to the next index for the comparison. So inside this for loop, what we will do is we will basically compare the value at this jth index, the value already available at this current index, because we need to find the perfect value which is smaller than already whatever we have at this current index. That's the reason why if at all, if the value at this current index, if it is greater than the value at jth index, then jth index has the smaller value. That means that current index should be updated with the j value. Okay, once we are done comparing all these values, right, the appropriate value for the index I is available at this current index position. That's the reason why once we are done, after completing the inner nested for loop, we will basically swap the value at ith index and the value at current index. Okay, so that's what we will be doing. Once we are done with the swapping, right, we will move on to the next index as we have outer for loop, and the logic will continue, and we will find the perfect value available in this current index, and we will swap it with the ith index. Okay, as a result, in the end, we basically got the sorted array. Okay, if you see this selection sorting algorithm, right, every time we are comparing, we are just trying to store the smallest value available index in some variable. We are not swapping then and there only. Once we are done with comparing all the available position values, in the end we are swapping only once. Okay, as a result, we are eliminating a lot of swapping operations, thus by bringing in the efficiency into this selection sorting algorithm. Okay, so that is the pseudocode of implementing the selection sorting to sort the values in the ascending order. If at all, if you want to perform the selection sorting for sorting the arrays in the descending order, all you have to do is change this greater than symbol to less than symbol, so that you will have a selection sorting pseudocode which can solve the, which can sort the array of values in the descending order. Now let's analyze the time complexity and space complexity involved in this selection sorting implementation. And this time complexity and space complexity also let's analyze in the best case as well as in the worst case scenario. When will the best case scenario of this sorting will occur? Whenever we have only one value in the array that we get in the input. If at all, if we have only one value, technically speaking, since it has only one value, it automatically it itself is sorted, right? But anyway, in the implementation that we are doing here, the length calculation will take only 1 unit of time, and whatever the outer for loop that we have written, right, this for loop is starting from 0 and executing for all the values. That means that the outer for loop basically gets executed once, and whatever the inner for loop that we have will not even get executed. As a result, the overall time complexity we have for the selection sorting algorithm in the best case scenario, where we are trying to sort the array which has only one value, will occur, and the time complexity is nothing but order of 1. Okay, and let's just try to analyze the same time complexity in the worst case scenario. In the worst case scenario, we obviously assume that there are n number of values in the array, right? Now obviously anyway, here reading the length will take only 1 unit of time. When we have n number of values, the outer for loop whatever we have written needs to run for all the indexes. That means that from 0 till n minus 1 it gets executed. As a result, the number of times it gets run is basically n, which is nothing but the size of the array. After that, initializing this current index will also take only 1 unit of time, and whatever the inner for loop that we are writing is getting executed from, in the worst case, it is getting executed from index 1 to till the last index, which is nothing but n minus 1. As a result, in the worst case, the inner for loop is getting executed for n minus 1 number of times. So based on the number of times it is getting executed, we can simply say in the worst case the time complexity will be order of n square. Okay, obviously if you try to calculate the memory consumed by the implementation that we are doing in both best cases and worst cases, if you see, we are using the couple of variables, and those couple of variables also we can declare them as a global variables inside the function, and we can reuse them. As a result, the best case and the worst case space complexity will be order of 1 only. Okay, and selection sorting anyway is one of the in-place sorting algorithm, right? Anyway, besides that, based on the implementation that we are going to do, will also the space complexity will be order of 1 only in both best and worst case scenarios. Okay, so that's all the information that you need to know while implementing the selection sorting algorithm.